What is the main motivation behind developing EURUS, according to the paper?
The main motivation behind developing EURUS, as stated in the paper, is to bridge the performance gap between open-source large language models, LLMs, and advanced proprietary models in their all-around capabilities to tackle a diverse range of challenging problems. This performance gap is primarily attributed to the lack of high-quality alignment data and the underexploration of preference learning techniques for improving models' complex reasoning capabilities. EURUS aims to address these factors by developing a suite of LLMs fine-tuned from Mistral 7B and CODELLAMA 70B, utilizing the newly curated, large-scale, and high-quality alignment data called ULTRAINTERACT. EURUS excels in solving challenging problems that require sophisticated planning, reasoning, tool integration, and the ability to interact with and learn from the environment and users, achieving state-of-the-art overall performance among all open-source models.
How does EURUS address the identified performance gap in open-source large language models, LLMs?
EURUS addresses the identified performance gap in open-source large language models, LLMs, by focusing on two key factors: the lack of high-quality alignment data and the underexploration of preference learning techniques for improving models' complex reasoning capabilities. EURUS consists of a suite of LLMs fine-tuned from Mistral 7B and CODELLAMA 70B, achieving state-of-the-art overall performance among all open-source models on diverse complex reasoning benchmarks. It excels in solving challenging problems that require sophisticated planning, reasoning, tool integration, and interaction with the environment and users. EURUS is trained on ULTRAINTERACT, a newly curated, large-scale, and high-quality alignment data, specifically designed to enhance ILM's reasoning capabilities. ULTRAINTERACT includes diverse instructions spanning math, coding, and logical reasoning problems, with preference trees that facilitate preference learning. By leveraging ULTRAINTERACT for supervised fine-tuning and preference learning, EURUS models demonstrate strong performance improvements, especially in math and multi-turn evaluations. Additionally, EURUS introduces a new reward model, EURUS RM7B, which achieves better correlation with human annotators than existing models, showcasing strong preference modeling performance on reasoning tasks. Overall, EURUS's comprehensive approach to leveraging high-quality alignment data and preference learning techniques effectively bridges the performance gap in open-source LLMs for complex reasoning tasks.
What are the key components of ULTRAINTERACT alignment data mentioned in the paper?
The key components of ULTRAINTERACT alignment data mentioned in the paper include 1. Diverse planning strategies in a unified pattern, such as sequential processing and tool creation, followed by executing step-by-step actions formatted in either text or code to provide diverse reasoning trajectories. 2. Multi-turn interaction trajectories with the environment and the critiqued to improve models' capabilities to learn from feedback and correct previous errors. 3. Paired correct and incorrect actions organized in tree structures to facilitate preference learning. 4. Each instruction in ULTRAINTERACT collects a preference tree, with the instruction as the root and each action as a node. 5. Trajectories consist of root-to-leaf paths with a sequence of actions. 6. All nodes of correct actions and all trajectories ending with correct actions can be used for supervised fine-tuning. 7. Paired correct and incorrect nodes or trajectories can be used for preference learning. 8. ULTRAINTERACT constructs binary preference trees for every instruction, with each action as a node. 9. The preference trees are capped at a maximum of 5 turns. 10. Additional correct actions are sampled for challenging problems with multiple ground truth solutions, along with additional incorrect actions to pair with them for supervised fine-tuning and preference learning.
How does ULTRAINTERACT facilitate preference learning for reasoning tasks?
ULTRAINTERACT facilitates preference learning for reasoning tasks by collecting a preference tree for each instruction, where the instruction serves as the root and each action as a node. This structure allows for the pairing of correct and incorrect actions, which are essential for preference learning. The preference tree includes diverse planning strategies, multi-turn interaction trajectories, and paired correct and incorrect actions organized in tree structures. These components provide a framework for models to learn from feedback, correct errors, and improve reasoning capabilities. ULTRAINTERACT's data quality ensures clear and objective preferences for correct actions, eliminating the need for ambiguous human or LLM-based preference annotation. By sampling paired correct and incorrect actions at each turn, and expanding incorrect actions into the next turn, ULTRAINTERACT provides data for models to learn from feedback and refine their solutions. Additionally, ULTRAINTERACT constructs binary preference trees for each instruction, allowing for comparisons at every turn and enabling models to improve their interaction abilities over multiple turns.
What are the differences in the performance of DPO, KTO, and NCA algorithms in the context of preference learning for reasoning tasks, according to the paper?
The paper highlights that the performance differences of DPO, KTO, and NCA algorithms in the context of preference learning for reasoning tasks are significant. DPO, derived from the Bradley-Terry model, optimizes the relative differences between chosen and rejected data, overlooking the absolute values of rewards. This leads to a decrease in rewards for both chosen and rejected data, ultimately hurting model performance. On the other hand, KTO and NCA algorithms show increasing rewards for chosen data and decreasing rewards for rejected data, leading to improved model performance. The distinction lies in the trend of rewards, where DPO focuses on relative differences, while KTO and NCA prioritize increasing the rewards of chosen data. The paper suggests that increasing the rewards of chosen data is especially beneficial in preference learning for reasoning tasks, as it positively correlates with performance trends.
How does EURUS ERM7B differ from other reward models mentioned in the paper?
EURUS ERM7B differs from other reward models mentioned in the paper in several key ways. Firstly, EURUS ERM7B achieves a better correlation with human annotators than all existing models on AutoJ and MT Bench, including GPT-4. This indicates that EURUS ERM7B excels in preference modeling performance on reasoning tasks. Secondly, EURUS ERM7B stands out as the best 7B reward model overall and achieves similar or better performance than much larger baselines. It outperforms GPT-4 in certain tasks and achieves a better correlation with human experts. Additionally, EURUS ERM7B improves ILM's reasoning performance significantly through re-ranking, consistently improving pass-at-1 accuracy across all tasks and performing better than a 5 times larger baseline, Starling ERM34B. Furthermore, EURUS ERM7B's training objective includes augmenting the Bradley-Terry objective with an additional term to directly increase the reward of chosen actions and decrease those of rejected ones, which has been shown to be beneficial in improving ERM performance on hard problems and reasoning. Overall, EURUS ERM7B demonstrates strong preference modeling performance on reasoning tasks and achieves impressive results in improving ILM's reasoning capabilities through re-ranking.
What datasets are used for evaluation of EURUS 7B and EURUS 70B models in the paper?
The datasets used for the evaluation of EURUS 7B and EURUS 70B models in the paper include HumanEval, MBPP, LeetCode for coding, GSM+, math, Theorem QA, SVAMP, and ASDIV for math, and BBH Hard for reasoning for single-turn evaluation. For multi-turn evaluation, the MINT dataset is used, focusing on coding and math problems. The evaluation metrics include pass-at-1 accuracy, for single-turn evaluation and success rate at turn 5 for multi-turn evaluation. These datasets were chosen to assess the model's performance in various reasoning tasks and to compare them with general-purpose and specialized models, as well as with previous models like GPT-3.5 Turbo and GPT-4.
What are the key takeaways from the evaluation results of EURUS models mentioned in the paper?
The key takeaways from the evaluation results of EURUS models mentioned in the paper are as follows. 1. EURUS, both the 7B and 70B variants, achieve the best overall performance among open-source models of similar sizes. 2. EURUS outperforms specialized models in corresponding domains in many cases. 3. EURUS 7B outperforms baselines that are 5 times larger, and EURUS 70B achieves better performance than GPT-3.5 Turbo. 4. EURUS's instruction following performance is among the best general-purpose models, substantially better than specialized ones. 5. Preference learning with ULTRAINTERACT can further improve the performance, especially in math and multi-turn ability. 6. KTO and NCA consistently improve the model's performance in all 5 math benchmarks and multi-turn evaluations. 7. DPO hurts model performance on most benchmarks, with the 70B model failing due to rewards going down to negative infinity. 8. The improvements in interaction ability should be attributed to ULTRAINTERACT rather than the algorithms alone. 9. EURUS ERM 7B stands out as the best 7B ERM overall, achieving similar or better performance than much larger baselines. 10. EURUS ERM 7B achieves a better correlation with human experts than all existing models on AutoJ and MT Bench, and it performs comparably to the 5 times larger Starling ERM 34B on Reward Bench.
How does the paper suggest improving the performance of models in preference learning for reasoning tasks?
The paper suggests improving the performance of models in preference learning for reasoning tasks by focusing on increasing the absolute values of rewards for chosen actions and decreasing those of rejected actions. This approach is based on the observation that in reasoning tasks, the space of correct answers is much smaller than that of incorrect ones. The paper highlights that the distinction in the trend of rewards between different preference learning algorithms, such as DPO, KTO, and NCA, plays a crucial role in model performance. Specifically, the paper indicates that algorithms like DPO, which optimize relative differences between chosen and rejected data, may overlook the importance of absolute rewards in reasoning tasks. By emphasizing the significance of increasing rewards for chosen actions, the paper suggests that this strategy can be especially beneficial in improving preference learning for reasoning tasks.
What is the significance of ULTRAINTERACT data in the ablation study conducted on EURUS 7B SF's performance, according to the paper?
The significance of ULTRAINTERACT data in the ablation study conducted on EURUS 7B SF's performance is crucial. The study evaluated 3 settings, using original ground truth answers, open source data only, and ULTRAINTERACT data only. The results showed that EURUS outperformed the ground truth model on all tasks, confirming the advantage of ULTRAINTERACT's design of divide and conquer and code as action patterns. Training only on open source data without ULTRAINTERACT significantly harmed reasoning performance, highlighting the effectiveness of ULTRAINTERACT. Conversely, training solely on ULTRAINTERACT led to a performance drop, except for BBH, especially in instruction following, indicating the necessity of mixing ULTRAINTERACT with other alignment data for better all-around supervised fine-tuning. Therefore, ULTRAINTERACT data plays a critical role in enhancing the reasoning performance of EURUS 7B SFT models, demonstrating its importance in improving the overall capabilities of the models.